3/4 of the audience. Everybody's out enjoying themselves somewhere in Belgrade. But I think that will go on, and if they want to see it, I understand it's being filmed, so one can look at it on the internet. So I think I shall start. Okay, so what I described to you before the break was a numerical technique, the conservative M integral or interaction energy integral, which can be used to calculate stress intensity factors with finite elements.
Which technique?
M integral or interaction. Here we go. We calculate the integral, we calculate the solutions sigma 1 is the sought after solution, and U1, and we have auxiliary solutions, and we calculate the integral, and in this case we're able to find K2, okay, and K1. So we use the M integral, or the interaction energy integral. Whoops. And we considered a very large body, so if you want to have, in finite elements you can't analyze an infinite body. Actually you can, there are infinite elements, but you can use a finite body, and if the crack length is at least, if the half width and the height are 40 times the crack length, you approach infinite body. So I'm showing you, we carried out this problem using symmetry. You have symmetry with respect to the transverse axis, or you can think of it as the y-axis. And so we only did half a mesh, and the crack is somewhere in here. It's small, and we had a coarse mesh and a fine mesh. And we did plane strain, and we used quarter point elements around the crack tip to give us a square root singularity. What it doesn't give us the oscillatory part, but it works fairly well. And we applied sigma 1 and sigma 2. This time we have plane strain, so we choose sigma 1. We apply a specific sigma, the far field tensile stress, and we have a relationship between sigma 1, sigma, and sigma 2. So we choose sigma 1, and we calculate sigma 2, and we apply them. If you don't do that, your results will be off, and you can really see that your results are off. Well, we have the exact solution, which was one I showed you earlier today. So K1 is approximately 1. I have a feeling it's normalized with respect to sigma square root of pi a. And K2 is much smaller, and it's K2 that's difficult to get because it's so much smaller than K1. And you can see that with the coarse mesh and the fine mesh, we did very well. As you increase the difference between E1 and E2, it gets more difficult to get a good solution. So if you want to see how well your finite elements are working, make this 1,000, and you'll see how well or poorly you're doing. Okay, so just to say, I know how to find stress intensity factors. So I'm saying you know how to find stress intensity factors. I can give you a method, and you can find the stress intensity factors. So now, one of the other things that we are concerned about when we have interface cracks is when we actually have a body, you have to do something to put those two phases together. So I'll show you a test with glass and epoxy. And epoxy, of course, you can just cure at room temperature. And so you would think that you were minimizing the residual stresses. The residual stresses are pretty high between glass and epoxy because of the difference between the mechanical properties. So what we also needed is a way of finding the stress intensity factors due to the residual curing stresses. And so we came up with an M integral for thermal stresses, thermal residual stresses, and you add this term. Beta relates to the the coefficient of thermal expansion and the mechanical properties. Epsilon are just the strains. In fact, they're the total strains, the strains due to mechanical loads and the strains due to thermal loads. And theta is the temperature difference. So when you cure it, let's say you cure something at 60 degrees Celsius and you bring it down to room temperature, so this is the temperature difference. And it only appears if there's a gradient in the x1 direction. So if it's just a constant temperature change, this term goes out, and you look as if you have the same M integral as you did for mechanical loads. But there is a slight difference. One of the differences is that sigma is you have the stress-strain temperature relation. Beta is related to alpha. And here is beta ij for, of course, you have to have a K on these for upper and lower, but beta ij is just related to Young's modulus, the Poisson's ratio, and the coefficient of thermal expansion, and this is the Kronecker delta, delta ij. And so we have the integral, and then we have the relation between M and the stress intensity factors. And so again, I'm not going to show you any details. Again, I could find the stress intensity factors due to residual curing stresses. And so we find K1R residual and K2R residual. And now I would like to tell you about tests. So these are Brazilian disc specimens, and I'll explain them further. The diameter of the specimens are 40 millimeters. We have an interface crack. I can't see anything here. I guess you can't see anything here too. On my computer, I can see I have two different materials, and there's a notch here created by Teflon, which is about 25 microns thick. And here we had Teflon, but we induced a natural crack there. And so we have epoxy, we have glass, we molded the specimens, and I don't know if you can see this, but there's a ring of aluminum which cut down on the residual tensile stresses at the end. The aluminum makes them compressive stresses, because what happened was, here we are doing experiments. I tell the technician, put the specimens on the table at night, and we'll come back tomorrow morning, and we'll be all ready to test 5 specimens. We come back in the morning, and they all have cracks. That was before we put the aluminum. We have all of them cracked here, because the temperature in the lab went down to like 16 degrees Celsius at night, and we came back in the morning, put on the heat, and we went up to 22 degrees, and that was enough to crack the specimens. In fact, by the time morning came, without putting on any heat, it was warm enough in the lab to develop cracking here. So the aluminum, we came up with that. Fortunately, aluminum and glass have very similar Young's moduli, so that is what kept the specimens together. So those are Brazilian disc specimens. So the ones on the left are glass epoxy, and the one on the right, which you cannot see, are 2 ceramic clays. And so here, okay, so you can see the specimen a little bit. This is very orange. This is a very sort of deep orange. And this is our loading frame, and you rotate the specimen. The load comes along the vertical axis, and we rotate the specimen, and we get a whole series of different mixed modes by rotating the specimen with respect to the loading direction. And now this is an old, we don't have this machine anymore, but this is an old picture. And here is the specimen. Actually, if you look very carefully, this isn't one of those specimens. This is a composite specimen. but we put it in the loading frame. This is the loading axis of the instron. At that time, we were taking pictures, we were taking videos, so that you can re-look at the experiments after you've done them, to try to look at it frame by frame, to try to pick out when did the specimen break. And now we even have better equipment than we had then, and we take data from the machine. Today we run the machine from the computer, and we store everything in the computer. We don't have videos anymore to put in a video machine. This is a bit old. So then we want to analyze the specimen. And so in the finite elements, I mean, the specimen was standing so that this was the crack, this was the interface, and we were loading in this direction. So for finite elements, it's easy just to put the interface here, and you load in this direction or in this direction. And so these were the finite element meshes for one of the analyses. And we found K1F and K2F due to applied loading. And we did a thermal analysis to find the residual Ks, and we superposed them so that we have a total stress intensity factor. And so KT1 is the total stress intensity factor, both to applied load and residual curing stresses. And same thing for K2. And so glass epoxy, the material that we used, epsilon was minus 0.088, Lecti had 0.06, and the two ceramic clays, the epsilon is very, very much smaller. It's on order of magnitude smaller than for glass epoxy. And I think I have the formula right. Here is epsilon, and here is G1C. We take for each specimen, we carried out between 20 and 30 tests. For each one, we calculate K1 hat, divide by this mechanical parameter H, and we take the average, and that's our K1C, which is given here. They're very low, 5.1 newtons per meter and 3.7 newtons per meter. Those are very, very low toughness values. But we're talking about glass epoxy and a rather smooth interface. So for the failure criterion, I'm going to go over what I showed you earlier. We take the sum of the squares of the hatted quantities, divide by, I'm writing here H1 because there's also a H2 when we do out-of-plane problems. It's the same H as before. K hat is the normalized K with this L hat, which here we will choose because we have experimental values, and this is the same H as before. And by manipulating this expression, we have GIC, given this in terms of 1 plus tan squared psi. And I remind you that we take the average value for each, we calculate this for each specimen, and we take the average value, that's our G1C average, and that's psi. And as I explained to you before, this is our failure curve. If GI in our structure is higher than G1C, we have failure. If GI is less than G1C, we should be safe. So above is failure and below is safe. And as I said before, we saw that the data, there was scatter in the data. So we looked to do something statistical, and we made the assumption that the G1C values have a normal distribution. And so the probability of unexpected failure in this zone is governed by the integral of the probability density function from 0 to ZP. ZP is the standard normal variant, and it's tabulated. So for example, if I want to say that the probability of unexpected failure is 10%, then ZP is given. There are tables. You can look up what ZP is. There's no mathematics to do. So we want to do something statistical, so we want to obtain a failure curve for which unexpected failure, we would be in the safe zone, is only 10% with a confidence of 95%. We use the G1C value, that average value, and we deduct from it. S is the standard deviation, and K is a factor of tolerance, one-sided tolerance. We only have one-sided. We're not doing a two-sided. And we just looked this up in a paper. We found this in a paper, and ZP is the standard normal variant, and P is the probability, and gamma is the confidence. And I didn't write down what those two values, ZP and Z gamma, are, but ZP I showed you, and Z gamma has a different value that you look up. And so that we then decrease G1C bar by KS, and we obtain a new criterion, which is lower. So this is our deterministic failure curve. And this is our deterministic failure curve when we have lowered G1C bar. And so then, from a statistical point of view, we have only a 10% chance of having failure in the safe zone with a 95% confidence with this mathematics. And so this is our G1C star. So let's look at the test data. So here's glass epoxy, and here's epsilon. We carried out 25 tests, so we had a sample size of 25. The standard deviation was 1.81 newtons per meter of our data. We calculated K. K depends on the sample size. As the sample size increases, K goes down. And so we had a value of G1C bar, and it was lowered from 5.1 to 1.8, which is a high price to pay. But now we have some statistical confidence on our results. And then for the two ceramic clays, we did a similar thing. We had 31 tests, and you can see that K has been decreased. And so this 3.7, again, we paid a high price. And now we can look at the data. So this is the data for glass epoxy, and the black curve is our deterministic curve, and you can see that there's lots of scatter. There are lots of points that are so-called in the safe zone, and we had failure. And we can see that G1C bar is 5.1, and now we decrease G1C to G1C star, which is 1.8, and we see that we have 1 point on the failure curve. All of the points are above the failure curve in the failure zone. So by using this, we now can say, for the next test that we do, or for the structure that you have, you only have a 10% of failure with a 95% confidence that your point will be below the curve. So this gives you some sort of a safety factor in analyzing the glass epoxy interface. Now, we did the same thing for the ceramics, and you can see we have a lot of scatter. And this is our deterministic curve, and we have many points below the deterministic curve. And then here is our statistical failure curve, that we only have a 10% chance of having a point below the curve, and we don't have any points below the curve, but we paid a heavy price of going from 3.7 to 0.9. So this is the way we approach interface failure and how we carry out the tests. And what I didn't say in all of this, but it's written here, here is your L value. And when we first started off, we don't know what L value to choose. We choose an L value arbitrarily, we graph everything, and we see how well do the points match up. I showed you an example where they didn't match up at all. And by trial and error, we change the L value until we get something that fits well. It allows us, it's a free parameter that we can use to make the data fit the curve. Are there any questions? In fact, I think I'm at the end, not at the end, I'm at the end of the first lecture, which we should have ended last hour. So we talked about interface fracture mechanics principles for isotropic materials. We looked at the stress and displacement fields. I showed you an example of a stress intensity factor, and I showed you a way of calculating the stress intensity factors. We talked about the interface energy release rate. It says here phase angles. We only talked about one phase angle. We talked about fracture toughness testing, a statistical analysis. We carried out fracture toughness tests, which I presented for the Brazilian disc specimen with glass epoxy and 2 ceramic clays. The specimens were analyzed by means of the M integral, both for residual thermal stresses and for applied load. And we looked at 2-dimensional failure curves, one which is deterministic, and we chose to look at one which predicts a 10% probability of unexpected failure with a 95% confidence. You can change those and you can see what you get. And so now I say, are there any questions? Yes.
I have one question about finite element analysis. You said that as the stiffness ratio goes up, then of course you will have a poorer solution. And what I was curious about is having a finer mesh would improve the solution, or
Yes.
it's just
No, yes, finer
ratio?
mesh, and you can improve the solution.
So
Of
it's-
course, we're doing it when we know the solution,
Yeah.
so you can see what's happening. When you don't know the solution, you have to do conversion studies and do at least 3 different meshes and see that you're getting convergence. Okay? Okay, we ready to go on? Delaminations. Okay, well, we're all flying in these plastic planes, and by the way, I get very nervous about going in these plastic planes because I feel I know how much they don't know and how much I don't know. And what they're doing for us is they're over-designing the planes. They're making them much heavier than they probably need to, so hopefully they won't fail. But we can see in this slide, which is a really nice example with the Airbus series, of how in the early 70s, 5% of weight of the plane was made of composite materials up until we come to the newest planes where it's over 50% by weight. So we are flying in plastic planes. Everybody calls those epoxies plastic, and of course, not to worry about the competition, this is a Boeing Dreamliner, a 787, and it also has 50% by weight of composite materials. So lots and lots of the structure is made of composites. And I think it was in 1973 because of the oil, but you're all too young, except for Professor Rice, to know the oil. There was an oil embargo in 1973 by OPEC. And so there was a real impetus in the United States to move ahead with composites because they're much more fuel, there's a tremendous savings in fuel, even with them being over-designed. So we ran ahead with composite materials. So for people here who have no idea what I'm talking about composite materials, there are different kinds of composites. I'm talking about composites where, unfortunately, the slides are not that, it's hard to see, but there's a whole bunch of fibers here. These are carbon fibers. You mix them with epoxy, and out comes, let's say, if all the fibers are lined up in this direction, out comes a transversely isotropic ply. Now, isotropic material have 2 independent mechanical properties, let's say E and nu, or mu and nu. Because if we have E and mu is dependent on E and nu. If you have transversely isotropic materials, it has 5 independent mechanical properties that describe it. So if we have all the fibers in this direction, and I pull on it in that direction, it's very stiff because the fibers, the carbon fibers, have very high Young's modulus. If I pull on it transverse, it's very weak. So E in this direction is different from E in the longitudinal direction. So there are 5 properties. There's E1, E2, G1, new one, and G2, and then you have G, the transverse G is related to E and U. Anyway, so I can make a ply, and plies like this are something like 0.2 millimeters thick, 0.15 millimeters thick, so they're very thin. And so I form a laminate by taking plies with fibers. They can all be in the same direction. That's called, I think you probably heard this morning when Dr. Blackman spoke. He must have spoken about laminates this morning. So I can put all the fibers, for example, in the 0-degree direction, and then I can put the next ply on there in the 90-degree direction, and so on and so forth. And I can lay plies up in different directions. I can put them plus 45, minus 45. I have all the choice in the world the way I want to line this up. So I just show this as an example. And so each ply is about 0.2 millimeters thick. So if you want to have something that's 3 millimeters thick, so you have, I don't know, something like 15 plies. So the problem with laminates is illustrated here. For example, each one of these parallel lines, vertical lines, indicate a different ply. Now I can have all the plies, let's say, with the fibers going in one direction, as I said, which is called a unidirectional laminate. Or I can have them so that one of the plies goes in 0 and it's going up and down, and in the other it's coming out of the wall, so it's in the 90-degree direction. And the problem with laminates is you can have cracks in the matrix. Now clearly, if these fibers are in the 0-degree direction, I'm not going to get this. I'm only going to get this if, let's say, they're in the 90-degree direction or the 45-degree direction. So this is matrix cracking. And we can have separation of the plies, which is called delamination. And that's what I'm going to concentrate on. The laminates are very prone to delamination, to a separation of the plies. It's one of the fundamental modes of failure in laminate composites, and it comes from material or structural discontinuities together with in-surface loads. It comes from impact. If there is a guy out on the wing and he's a mechanic and he drops his hammer or his wrench or something, he can create a bunch of delaminations through the thickness of the laminate, and that's not a very happy situation. As I said, delaminations tend to occur between plies of different orientations. Unidirectional is less prone to this. They have used high safety margins to design composite structures. And if we can give the engineers in industry accurate methods for getting the fracture toughness values, this can help in structural integrity. We actually need 2 things. We need the fracture toughness to talk about catastrophic conditions, and we also need fatigue data, and we would want to go in what's called a damage tolerance direction. There are problems with that. I'm not going to go into that right now, so I'm only going to talk at this point about fracture toughness, and if we can give accurate fracture toughness values, we can aid in predicting failure, as we do with metals. So now I'm going to talk about resilient disc specimens, which have a strip of composite material. These are the same as the specimens I showed you, glass epoxy. They're 40 millimeters in diameter. We have a notch made by Teflon of between 10 and 25 microns. And here, schematically, you can see fibers. We have a layer of fibers in the 0-degree direction, in the 90-degree direction coming out of you, those are the dots, and the others in the 0-degree direction. And this strip is about 12 millimeters in width. And we have specimens, and I didn't say that earlier, but those other specimens were also 8 millimeters thickness into the paper. And we fill this out with aluminum discs. It's really for handling purposes. You can't put the specimen in the machine if you just take the strip. Even though you may be only loading on the strip, you can't accurately put it into the machine. So we need the aluminum half discs. And so Israel Aerospace Industry made us a plate of material with this layup. It's 4 millimeters, 4 millimeters, and 4 millimeters. And from the plate, we cut out strips and we glue them into our aluminum discs. And when we finished the plate, I said to them, make me another plate. So this is what's called a symmetric composite, because it has a symmetry line down the center. You know, if I just lay the plate out. And the first plate was bent, and it shouldn't have been, and the second plate was bent, and the third plate was bent, and then they said, you know what, we'll do something else. So they made a laminate where there were 1/2 millimeter, this is 0, 90, 0, and outside they laid up about 5 millimeter thick plates, plus 45, minus 45, to keep everything so it wouldn't bend. So, of course, theoretically, these two results should give you, these two layups should give you the same results, otherwise you don't have a fracture toughness parameter. That this is 1/2 millimeter each of the plies, and this is 4 millimeters. If fracture mechanics really works here, then you should get within the scatter the same results. So I didn't sleep until we did about 10 specimens and analyzed them and saw that they do give us the same results. But there were a number of sleepless nights. So anyway, in addition to doing that, we looked at the interface, plus 45 degrees, minus 45 degrees, and here you see many different colors, each color signifying a different direction. But if we just focus, if we can, focus on the interface delamination. On one side we have plus 45 degrees, and on the other side we have minus 45 degrees. And then they're all different. They're 0 and 90 and plus 45, minus 45. We have all different ones here. So we carried out tests on these specimens, and we carried tests out on those specimens. And just to make sure the 0-90 is clear, if this is the X1 direction, the X1 direction goes along the crack, and so 0 is going in the X1 direction. So these are the 0-degree layers, and 90 is perpendicular, and it's coming out. You can't see this, but this is X3. Unfortunately, the whole slide doesn't come in. And then plus 45, minus 45 is here. We have plus 45 with the X1 axis and minus 45. So the fibers are coming out at some angle from at a 45-degree angle from the specimen into space. Well, here we go again. That's why we lost half the audience, because of this initial slide. The solution looks exactly like the one in which we had two isotropic materials, and now we have 0 and 90, and it looks exactly the same. Alpha beta is 1, 2, K is the upper material, K equal 1, 2 is the upper and lower materials. We have R, we have 1 over the square root of R, and we have R to the I epsilon in the same way as we had before. We have this complex stress intensity factors, and then we have these functions. And these functions we can write analytically, and I've done it myself, and I've had students that have done it. They can, if you write them out completely without using some symbolism, you can fill up a whole page with one of these functions. They take a page, but they're functions that are easily written. They're cosines, coshas, and so on and so forth, but much more complicated than for the two isotropic materials. Epsilon, again, is the oscillatory parameter, and we have, for the 090, we have the in-plane ones with K1 plus IK2, and then we have a normal mode 3 stress intensity factors. We also find this function from the Stroh formalism. And we go ahead in the same way as we went before. We normalize the stress intensity factor with L hat. And now we have two phase angles, or two mode mixities. We have K2 to K1, K2 hat to K1 hat. And now we're comparing K3, this phi, with the sum of the squares of the in-plane stress intensity factors. Now we have H1, here we have H1 and H2. And now all of a sudden you have epsilon, which you know, that's the oscillatory parameter, and all of a sudden I've thrown these D's at you. They're functions of the mechanical properties that you obtain when you do use the Stroh formalism. And now here is the interface energy release rate, and now we have a three-dimensional one where we have K1, K2, and K3. For general anisotropic material, you can have as many as 6 stress intensity factors. You can have K1, K2, and K3 with the Arabic numbers, and you can have K1, K2, and K3 with the Roman numerals. The Roman numerals are multiplying a square root singularity, and the Arabic numerals are, the Ks are multiplying the singularity with the oscillatory the oscillatory square root parameter. We have one paper where we had 5 stress intensity factors, so we learned about it. At first we looked at it, and in fact, the plus 45, minus 45, K1 and K3, I don't go into this when I get there, K3 turns out to be multiplying the square root oscillatory parameter, and then we have K2 that's multiplying the square root singularity. And when we submitted that paper, we got it back that we were wrong, that it can't be, the K3 can't be over here, it has to be over here. But it was right, and eventually the paper was accepted for publication. So here again we have a mechanical integral. It's exactly like the one we showed you, except now the asymptotic solutions are quite different, but we have them. And so we obtain K1F, K2F, and K3F because of applied load. And then we have a thermal M integral, and we get the stress intensity factors for the residual curing stresses, K1R, K2R, and K3R. We superpose them to get a total stress intensity factor, and now we have the interface energy release rate G for K1 squared, K2 squared, and K3 squared with a total on them. And we have the two phase angles, psi hat and phi. So here are the specimens with a 090 interface. You can see them in actual fact. And this was for plus 45, minus 45 degrees, and we're using a carbon epoxy, carbon fibers in an epoxy matrix. AS4 is the carbon fiber, and 3502 is the epoxy. And we have a volume fraction, I didn't really go into that, a volume fraction of 62%. So you measure the volume fraction of how many fibers you have in the matrix. 62% is, 60% is common. People don't use them with 40% or 20%. They go up to 60% because the carbon is what holds the load. That's the the matrix is there just to hold the fibers together. So I earlier said that the material, like when we had 0 fibers in the 0 degree direction, that it was transversely isotropic. Well, it's effectively transversely isotropic because obviously it's inhomogeneous, but we sort of average the properties over the material. We use a micromechanical model in order to get, we convert it to anisotropic material, which is homogeneous, even though it really isn't homogeneous. We get the average properties. So we don't look at the fiber and the matrix, we look at the whole thing, and clearly the properties depend on what the volume fraction is of the carbon fibers. So here again is the loading frame, and when you put this in and you rotate the specimen and you load in this direction, you get different mode mixities. And here is our experimental setup. We have an instron. This is our current instron. We have a video microscope, and we have a specimen in here, and we film the test, and then we look at the test frame by frame, and we're able to see when the delamination propagates, at what load it propagates, so we get the fracture load. And so now we have the 3D failure criterion, so we're going to write GI in terms of K1, K2, and K3. I remind you that K hat is K L hat to the I epsilon. H1 and H2 are related to mechanical properties, and you can manipulate this to get this expression, so that GIC is a function of psi hat and of phi, which I show you here and here. And G1C, we take our specimens, we average all the K1 hat values, we square all the K1 hat values, divide by H1, and take the average, and that's G1C bar. And now we have a failure surface. So below the failure surface, we're safe, and above this failure surface, we expect failure, and we have scatter, and we deal with the scatter in the same way we did in the two-dimensional case. We use a statistical method to lower the curve, or the surface. So this is the 0-90 interface. Now epsilon is not that simple expression that I showed you for two isotropic materials. It comes out of the Stroh formalism, but it's a small number, and no one, if somebody wants a challenge in the audience, no one has bounded epsilon for anisotropic material. We see by examples that we get small values. This is for the 0-90 interface. This is extremely small. This is practically, Hutchinson would certainly say this is isotropic, but it's not isotropic. We keep it. N are the number of samples. With the 0-90, at that time, we did only two-dimensional analyses. And so we had 24 tests, so our sample size is N. This was G1C bar, and this was the standard deviation, 11.5 newtons per meter, and K is 1.84. So we reduce G1C from 26 to 5. In the plus 45, minus 45 degree problem, we did do three-dimensional analyses. We had 26 specimens, and we had 21 values of K along the delamination front. So we have 546 values, and you can see how this parameter K is influenced by the number of samples. So it went way down. You still paid a price, but not the same magnitude of a price of getting a 10% probability. So here are the results. The black curve is our deterministic curve. This is for the glass epoxy, this is for 0-90. You can see that G1C bar is 26.5, and we've worked on L in order to center our data. And really, you can see the data up here, how well it fits the failure curve. I mean, this data and the previous data, I didn't point it out with the glass epoxy, this data really is convincing that there's something to this failure curve because of how the data is sitting about it. Anyway, we don't like these points below, and we use two types of specimen, and the scatter from these specimens is sitting in the scatter from the other specimens, so we felt we really do have a fracture criteria. We really do have critical properties. This is the curve for which any next test or structure that you calculate will only have a 10% probability of failure below this curve. All the points went above this statistically obtained curve, but of course it's a big payment. We went from 26 to 5 newtons per meter, and that's a very big payment. And we did the same thing with the plus 45, minus 45, but now we have a three-dimensional failure surface. So above, it doesn't want to give it, doesn't give it to me. Okay, so this is our failure curve, a failure surface. These are our data points as a function of G1C. Here you can see it's kilonewtons per meter. This is 4 kilonewtons per meter. This is our data. Some of the points are below, some of the points are above. We had 26 specimens. We had 2 specimens for which all the points were below, and we had 6 specimens for which all the points were above the failure surface. And the rest of the points, if you go along the delamination front and you plot the points, some points are above and some points are below. So we told a story. In fact, my thesis advisor says you always have to tell a story. So the story was that some of the points along the delamination front reached failure. So they're going to start to propagate. The others that didn't reach failure are going to be dragged along by the momentum of the rest of the delamination propagating. So we only really had a problem with 2 specimens where all the failure points were below. We're in the safe zones. So if you notice, this is 4, okay, and we have a G1C of 92.4. So when we used our statistical analysis, in the next slide, you can see that the surface has been lowered. Now my highest value here is 3 kilonewtons per meter, and we've paid a price, of course. And the price is that now G1C is not 92, but it's 51 or 52. So we've paid a price, we've lowered this, but now all of the points are above or on the failure curve. So this is the failure curve that we will want to present as predicting a 10% possibility of failure below the curve from my structure with a 95% confidence. Okay, we're going till 3. I have more slides, not to worry. Okay, so we've talked about interface fracture mechanics principles for anisotropic material, and we've applied them to laminates. We considered the Brazilian disc specimen, and we had 2 different interfaces. One where we had a delamination between a ply that had fibers in the 0-degree direction above, and below is in the 90-degree direction. And in the other case, we had above plus 45 and minus 45. We used a conservative M integral to obtain the stress intensity factors for applied load and for residual curing stresses. And we have 2- and 3-dimensional failure curve and surface. One is deterministic. The other predicts a 10% probability of unexpected failure with a 95% confidence. And we are continuing with other layups, and on Wednesday, I have a student who will talk about, I really left out a lot of things. I have a student who will talk about an interface in which the upper layer has fibers in the 0-degree direction, and the lower layer, the lower ply, is a woven composite. It's woven just like your shirt is woven. And they're using a lot of them today in structures in airplanes. Maybe I will say one thing before I leave. These materials that we looked at were made by what's called a pre-preg process. What is done, and I think I do have a slide in the next part of the talk which mentions it a bit. I went to Israel Aerospace Industries, and they have, it looks like a roll of paper towels, like in the kitchen, paper towels. It's about this wide. and the fibers are already inside, and the epoxy is inside, and it's dry. They have some process where they infiltrate the epoxy into the fibers, and they process it, they cool it, they heat it, they heat it, they cool it, and out comes this dry material. And then the technician that's going to build some structure has instructions. He has to, I saw they had a whole big wing, and he put them in the 0 degree direction. Then he put them in the 90, he lined them up in the 0 degree direction, then in the 90 direction, then in the plus 45, and the minus 45, and so on and so forth, until he had the layup that he was instructed to make. And then they take this part and they put it in an autoclave, and they put it at a certain temperature and pressure, and the epoxy melts, and then the plies glue together, and then out comes your, after a while, out comes your structure. You know, they have to raise the temperature by 5 degrees and stay 10 minutes and another 10 degrees and so on and so forth. They have a recipe. They know how they're supposed to do it, and out comes the cake. So that's the way these specimens or this material is made. Now, my student who will talk about something called a wet layup. And so in a wet layup, they have like a woven material, so you know it's woven, and I can put it down so that they're called tows or yarn. You put it down, and it and you have the yarn in, let's say, the 0-90 direction, and you put it down, and now somebody comes and he puts epoxy on with a brush. So he had a fight with his wife, so he's just throwing down that epoxy, or he's in a very good mood and he's singing and he's putting down the epoxy, or he's putting very little epoxy. It's very, there's lots of voids in the material, and it's just not made like a prepreg, but a prepreg is much more expensive. And so she has plus 45, minus 45, and then she has 0 degree direction. Well, it's called a unidirectional fabric. Unidirectional fabric. All the carbon fibers are in one direction, and spaced throughout are a few glass fibers in the perpendicular direction, because all the fibers were just in one direction, the carbon fibers, and I picked it up, all the fibers would just fall on the floor. So the glass fibers hold it together. So she will show you pictures of that, and so it was with a wet layup. And so if we saw scatter here, she's going to have plenty more scatter in her results. But that's the material. That's the material. So as I say here, we're working on different layups, including woven composites. We've also done tests on woven composites where the weave was 0-90 and above was plus 45, minus 45, 0-90, plus, and so on and so forth. And we're still working on these. And we also moved over to fatigue delamination propagation so that we can have some sort of a damage tolerance methodology to lower the critical properties that are used in order to design structures, in particular aircraft. So this finishes the second part of my talk, and so I'll open up for questions, and then I'll talk about fatigue a bit. So, are there any questions? Everything is clear, everything is cloudy. Okay, let's be optimistic, we're clear. So now I'd like to talk about fatigue delamination propagation, because we've also worked on this. We'll talk about the motivation, the materials in the specimens, which are different from the Brazilian disc specimen. We'll talk about constant amplitude fatigue tests for different R ratios. I'll explain what an R ratio is. We'll look at the results. I don't know if we'll get to the Hartman-Skyver representation, but we may, and several conclusions. So now we're talking about composites, but we're going to apply fatigue. And so that means we're going to apply cyclic loading, maximum, minimum, so on and so forth. And this is how you design airplanes. You look at you take a structure, you assume you have a crack in it in a certain place, I'm talking about a metal structure. You calculate how many cycles until failure. Either I have to redesign because I have too few cycles, or I can go with it. Now, of course, there are big databases that the companies and the U.S. Air Force and other air forces have created to do analyses for different types of aluminum, steel, titanium, and so on and so forth. And now we're getting to composite materials, and we have to do similar things. So where are cracks going to occur in a composite? This is a figure for a laminate. So we have an edge effect. You have a singularity, even though there's no crack here because of this edge effect. You have a problem if you have a hole. This is the hole, and you have a singularity here. You have this ply drop. There's a singularity here, and so on and so forth, so that you have a tendency to have cracking or delamination begin at these structural regions. And you can also even get local buckling. You can have the laminate open up and have local buckling. So there's all kinds of problems with composites and fatigue. So here we're assuming that we have an aircraft, and we said before that modern aircraft today are 50% weight composites, so there's lots of places for these delaminations to occur. And here's an example. We have an external ply drop, and you can see, I don't know if you can see, but there are different plies here. You can see the lines. And so a crack has started, has come in, and gone along the interface between two different plies of carbon epoxy material with fibers in different directions. And this is what you need to predict. You have to predict how many cycles can this plane fly before we have to repair it. So aircraft industries have spectra of the kinds of loads that they expect their aircraft to sustain. And what they do is they put them in blocks. So here I have a load, I have maximum and minimum, and I have a number of cycles that I would like to say that the plane will endure. I don't use the spectrum, I form it into blocks. And so then I can talk about RP. It's the R ratio for applied load, P min versus P max. It's called the cyclic load ratio. So not only do I have the maximum load to worry about, I have this RP that I need to worry about. And then I have RP2, it's a different RP, and RP5, and RPN, and I want to predict. So that means I'm going to have to go and do tests at each one of these RP. Well, I'll never finish, so I can't do it that way. I have to find a way to do several tests at different RP ratios, and then from those I can predict the other RPs. It won't be exact, but it's some compromise. So I'm going to say I'll do 4 RP ratios, and I'll be able to do predictions for NRP ratios. And so here I'm showing you a weave, and I think it's pretty clear. You can see that this is a woven fabric. It's carbon epoxy. And then you can see it's called a plane weave, and in fact it's called a plane balanced weave. A plane weave just means under and over in both directions. And it's balanced because the fibers in the 0 degree direction, the volume fraction of fibers in the 0 degree direction are the same as in the 90 degree direction. And you can see that the yarn is about 2 millimeters wide. And this is from Hexcel, from their site. I don't think you can see it clearly, but they have a whole process to prepare this pre-preg, and at a certain point they impregnate the resin, and at the end out comes the dry material. It's this weave, and it's ready to be laid up and then put in an autoclave. So the material that we looked at was carbon fibers, G0814, and 913 is the epoxy. We have 15, our laminate is composed of 15 plies. It was manufactured in an autoclave. And so one layer, one ply, has the toes or the yarn in the 90 direction, and the one below it is rotated to be plus 45, minus 45, and maybe you can see it here. This is our laminate. Each blue layer is 90, and each red layer is plus 45, minus 45. So if you're looking here, this one is coming, the fibers are coming out at you. This is at the 90 direction, and the fibers are going along here at the 0 direction. And we've put in a piece of Teflon. I think it was 25, yes, it was 25.4 microns between the 7th and 8th layers. And this is our artificial delamination. And we're going to carry out tests on double cantilever beam specimens. So this is the length of the specimen, which is between 200 and 250 millimeters. We have what are called piano hinges where we apply the load, and we have all the different geometric parameters. The height here is about 3.6 millimeters, the width is 25 millimeters. We have the length of the initial delamination made by the Teflon insert, and we're following ASTM and ISO standards for carrying out these tests. Now, in those standards, it's only for unidirectional material. We're using this as a basis. We have multi-direction material, which leads us to our interface delamination. And I'm not going into detail because I want to go to the fatigue test, but this is the R-curve behavior. We carried out 5 specimens, 5 tests to get the G1R delta A behavior. So we have initiation of around 600 newtons per meter. It rises very quickly to an asymptote, which is about 710 newtons per meter. So this is what's called the G1R curve. This is our fracture toughness, but it's a function of crack length. And we carried out the fatigue tests in our loading machine, and you have all the details here, which I think I'll just skip along. You don't use, the loads are so small. The load cell here, for example, is 250 newtons. These specimens take very small loads to propagate. In the fracture toughness test, the maximum load was around 60 newtons, and here we get up to around 40 newtons, and it just decreases. What we do is we impose displacement. If you start to impose loading, the crack is either going to run ahead or it's going to stand there for 2 million cycles and go nowhere. So you use displacement and you propagate. You do an initial propagation, like in a fracture toughness test, and then you start, from those results, you start the fatigue testing using displacement control. So I talked about a load ratio. We also have a cyclic displacement ratio, D min to D max. And this D is the movement of the actuator. It's not a COD. So we carried out 8 constant amplitude fatigue tests using 4 different displacement ratios, RD of 0.1, 3.3, 5.5, and 0.75. And I hate tables, but I'll go through it very carefully. This is RD. We had 2 specimens at RD is 0.1, 2 specimens at RD at 0.33, 0.5, 0.75. So we have a whole bunch of RD. And then the RP, theoretically, they should be the same. But the slack in the machine is such that this is the average RD. It's settled down basically to these values after 10,000 cycles. And you can see that the number of cycles that these will run, our aim was to get to 3 million cycles, and we didn't always reach that. And when you run these tests, you have to run them 24 hours a day, 7 days a week. When we first started doing this, we have a paper where we ran them, and I said, okay, it's nighttime. Let's take the specimen out, put it in a container for maintaining temperature and relative humidity, and we'll come back tomorrow and we'll put it in. Well, when you put it in, you don't put it in exactly the same place. It moves. The displacements are so small that it moves, and so you get a lot of scatter in the results. But I was loath to leave the machine on for 24 hours a day. Oh, what's going to happen in the middle of the night? Well, it runs in the middle of the night and everything's fine. You come in the morning and we take crack lengths, we take pictures. So it's only after we finish the test do you look at the delamination length from the photographs. So it works automatically. The machine stops for a half a second, a photograph automatically is taken, and it continues cycling, and it works very well. And you can see the frequency of the test. The higher the frequency, the shorter the number of days, but the higher the amplitude, the lower RD is, the higher the amplitude is, and the lower the frequency has to be. Otherwise, you start hearing lots of noise in your machine. So we went from 4 hertz to 6 hertz. And what you want, in metals, you have the ADN as a function of delta K. And here, everybody started off with G. And it's a problem. That's the energy release rate. So using G is what started. And you can use for your function G1 max. Or you can use for your function delta G1 effective. And you recall that we use delta K for metals, and G is proportional to K squared. So if you, if you look here, basically, you have K max, it's the square root, minus K min. So this is going to be a good parameter to use, and this is not such a good parameter to use. And I'm getting toward the end, so I'm just going to show you some data. Okay, this will be my last slide. I'm not going to show you everything, but what you can see is you can see the ADN, millimeters per cycle. This is on a log-log plot. And this is G max. The hat just means it's normalized with respect to G1R. And so we had 2 specimens at 0.75 RD, 2 specimens at 0.5, and then the 4 specimens at 0.1 and 0.33 are overlapping, and it's something we can say something about it. But this is the kind of data that you can get, and we've moved forward with this, and we can do predictions with this kind of direction. And I don't have time to go into it all. But this is what a lot of people are working on right now, fatigue of using these different specimens. DCB is for mode 1, and there are 2 mode 2 specimens, ENF, edge notched flexure, and CLS, calibrated and loaded split. And then there are 2 specimens that are being used, mixed mode ELS, MMELS, mixed mode end loaded split. That ISO is working on it. And then there's another one, there's the MMB, mixed mode bending. And so lots of people are working on this to try to find a way forward so that we can use this type of data to make predictions, fatigue predictions for aerospace structures. So I'm going to stop here and entertain any questions. If you, I know what you're talking about. I don't know. Harris's law. There are 3 stages in metals that people talk about. 3 stages of fatigue crack propagation. Stage 1 where it's growing from a threshold, stage 2 in the Paris law region, and somebody said, don't say Paris law, Paris formulation. It's not a law, it's an empirical formula. And then there's stage 3 where it's going to failure. And yes, you can too, and the same thing here. It's very hard to get to threshold. So some people have defined threshold as when the ADN is 10 to the minus 10 millimeters per cycle. They took it from metals. But we get much lower values when we extrapolate. We have a method for extrapolating to the threshold values. So the answer to your question, yes. And the kind of thing that I was looking at in this slide, at the end, we're getting a bit of it's going to an asymptote to the 3rd region. And down here, we're going to to a threshold. And maybe here, I can show you here, schematically, and this is I think this is G1 max. Yeah. Schematically, the curves as R increases, the slope in the Paris region increases, and the threshold, you can see the various thresholds for the different R ratios, and they're all going up to this asymptote, theoretically, to G1R or G1C. So the answer to your question is yes, indeed. Well, if anyone wants to ask me questions during the break, we have a break coming up. We can all drink some coffee or water or whatever. And then we all go down, I believe, I don't know if it's down, but we go to Amphitheater A for the next lecture in a half hour.
Next lecture in half hour is full course below Amphitheater A at the entrance of the faculty, basically. So just go downstairs. And we will start